at the heart of the equilibrium topic is the law of mass action. And I don't know if you've heard of the law of mass action, have you?
Yeah.
You have? You don't sound very sure.
Maybe. It sounds like physics.
So, the law of mass action essentially states that for any reaction where the little a and the little b and the little letters are the coefficients, and the big A and big B are representative of different compounds. So, it states that for any generic reaction like this, the equilibrium constant for that reaction, when this reaches equilibrium, it will have a constant value that is equal to the concentrations of the products raised to the power of their stoichiometric coefficients divided by the concentration of the reactants raised to their stoichiometric coefficients. Okay.
Yes.
So that looks familiar, right?
Yes.
Okay. So that's called the law of mass action. Law of mass action. In case the proper term was not actually given to you. Okay, so why is this relationship valid? Well, it's because at an equilibrium, and I should have actually drawn this as a double arrow, in equilibrium there is a forward rate constant and a reverse rate constant for this. And this kind of goes back to rate of reaction. Well, at equilibrium, the forward rate and the reverse rate are equal. So if we do rate forward, or rate 1, is equal to K1 times the concentration of A raised to the little a power times concentration of B raised to the little b power. Assuming it's a elementary rate equation, it's not a more complex mechanism. But even the truth is, even if it's not, this relationship still holds valid when you set up the ratio here. But rate -1, the reverse rate, K -1 times the concentration of C to the C power, D to the D power. Essentially, the equilibrium constant is set up this way in order to give you a ratio of products over reactants. Because if it's greater than 1, an equilibrium constant greater than 1 will give you an indication that there are more products than reactants. That essentially the products tend to dominate the equilibrium. And the equilibrium constant likewise less than 1, very much less than 1, will indicate that reactants dominate. So if you actually set this up and you divide this rate by this rate, since these two rates are equal, effectively you get 1, and it'll be like this over rate. One. K1. A. B. Or B. Okay, and essentially, since these two rates are equal, they effectively give you 1. So 1 is equal to K to the -1 over K to the +1, and times C to the C over, or times D to the D over A to the A and B to the B. Okay. The really interesting thing about this is that we don't necessarily know what the rate constants are, but if we multiply both sides, if we multiply both sides by the reciprocal of this, okay, if we multiply both sides by the reciprocal of this gives you k1 over k negative 1, k1 over k negative 1. And that effectively cancels this. And you see that, in fact, the equilibrium constant here is equal to the rate constant of the forward reaction divided by the rate constant of the reverse reaction. So, K1 over K negative 1. Useful thing to keep in mind. So now that we have an idea of where this equilibrium constant comes from, and where this kind of pattern comes from, and how we can potentially use it, and how it relates to rate, let's look at how we can actually use it. So, for the first example problem, it says the equilibrium constant for the following reaction is Kp equals 1.48 times 10 to the 4th at 1000 Kelvin. Now, just as the rates change with temperature, because temperature affects the rate constant, right? So just as rate changes with temperature, equilibrium constants also change with temperatures. That's an important thing to keep in mind. Okay, so it says calculate Kp for the given reaction, for the reaction given by the following equation. It says equilibrium constant for the following reaction, Kp 1.48 times 10 to the 4th at 1000 Kelvin. So this is the given reaction that says the Kp is that value. So 2NO plus O2, whoops, O2, gas, I don't know what I was thinking, goes to form 2NO2. Okay. So then it asks us for part A that we have to solve for what the equilibrium constant is for this reaction. 2NO2 is in equilibrium with 2NO plus O2. Of course, this is a gas as well. Okay. What's the difference between the given reaction and this reaction? What'd you say?
Maybe just reverse.
It's reversed, exactly. So the Kp for the original reaction is 1.48 times 10 to the 4th, or basically 14,800. Okay? So if you flip, now one way to see this clearly, if you flip the reaction, what are you going to do to the K? You're going to flip it. So it becomes what?
1 over 14.
Exactly. So the Kp for the new one is going to be 1 over 14,800. Now, here's the deal. If you look at the equilibrium constant for the original reaction, you can see this more clearly. Kp is effectively the pressure, equilibrium constant in terms of pressure, is the pressure of NO2 squared divided by the pressure of NO squared times the pressure of O2. And if you're looking at the equilibrium constant in terms of pressure for the second equation, it's Kp is equal to the pressure of NO squared times the pressure of O2 over P NO2. So since these two expressions are the inverses of one another, it makes sense that you would take the inverse of the value of the first one to get the second one. Now it says, does the equilibrium favor NO or and O2, or does it favor NO2? Does it favor nitrogen monoxide and oxygen, or does it favor NO2? And which equation tells us that?
Favorite NO2?
Favors NO2?
Yeah.
Which equation tells us that?
The second one? Oh, like, between these two, are you asking
Between the two, yeah.
I think.
Trick question they both do. Basically, this one is large, is much bigger than 1, right? So that means the products are heavily favored. The product in this case is NO2. This one's very, very small, which means the reactants are heavily favored. But the reactant in this reaction is NO2. In both cases, they're telling you the same thing. They're just telling it to you from a different perspective. Does that make sense? Cool. Let's do number 2. It says, consider the equilibrium below. Na2O and SO2 is an equilibrium with Na2SO3. It said, write the equilibrium constant expression for this reaction in terms of partial pressure. I'm going to go ahead and erase this. Bye-bye. And we'll write our beautiful new equation. Na2O solid plus SO2 gas is an equilibrium with sodium sulfite. Okay, cool. So, what is the equilibrium constant expression for this reaction in terms of partial pressure? Any ideas? So, the equilibrium constant expression is that ratio of reactants over products, right? And this is in terms of pressure. So what's Kp? What would be the expression for that, for this equation?
SO2
You said what?
is, would it used to be SO2 by itself?
Not quite.
It's the RT delta N.
You're thinking about the conversion between Kc and Kp.
Oh.
That's a different equation. We won't deal with that yet.
Okay, question. Because those two are solids, we don't have to consider them. We don't have to consider them, right?
Very good. You would not have to consider them.
But it's 1 over SO2.
So it'd be 1 over the pressure of SO2.
Yeah.
It'd be 1 over the partial pressure of SO2. Good. Do you know why we don't consider solids? Now, the part of it is, okay, in terms of pressure, solids don't exert any pressure, right? If you're thinking about it in terms of concentration, what's true of the concentration of a solid? Does it change? No. Solids are incompressible, right?
Yes.
So you can't, generally speaking, crush them into a denser formation. So because they're incompressible, the density of solid is their concentration. And the concentration doesn't change. And so since it doesn't change, we can kind of ignore it because it's not really purposeful. In terms of, in slightly more accurate terms, when you get into analytical chemistry, the real reason is that solids and liquids tend to effectively have what's known as an activity of 1. In truth, these equilibrium constants aren't properly speaking about pressure or concentration. They're really about activity. It's just that the concentration is proportional to the activity, or the pressure is proportional to the concentration, which is proportional to the activity. So we can't give equilibrium constant in terms of either pressure or concentration, but it's really the activity that we're concerned about. But this is why equilibrium constants never have a unit. You notice how this is supposed to be a pressure, right? Why isn't there a pressure in the answer, so to speak? If we were looking for the Kp. Because we're not actually looking for Kp per se, we're looking at the activity. And activity is a unitless quantity. So, write the equilibrium constant expression for this in terms of partial pressure, we just did. Now, why doesn't the concentration of Na2O appear in the equilibrium? We already talked about that. Alright, so we're going to go ahead and skip to number 3. Is that good?
Yes.
Alright. A flask is charged with 1.500 atm of N2O4 and 1 atm of NO2, and the following equilibrium is achieved. And by the following equilibrium, I mean, I need to write it down. N2O4. Equilibrium with NO2. Alright. It says after equilibrium is reached, the partial pressure of NO2 is 0.512 atm. What is the equilibrium partial pressure of N2O4? So in a problem like this, anytime it gives you initial concentrations and it wants you to solve for equilibrium concentrations, you're probably going to need an ice chart. You're probably going to want to use an ice chart. And an ice chart, have you gone over ice charts yet? Mm-hmm. Okay. So that's how you know you need an ice chart. If you're given initial values and you're asked to solve for equilibrium values. Now here's the other thing. If you're given just equilibrium values, are you going to need to use an ice chart?
No.
Probably not. Because if you're just given equilibrium values, you can usually just plug those into the form or modify them somehow, but you're probably not going to need to use an ice chart. Because an ice chart is about comparing initial values to equilibrium values. And you only have to use one if you're comparing initial values to equilibrium values. So the initial values here are 1.5 for N2O4, ATM, and 1 for NO2. Now what's the change going to be? Well, before we can actually figure that out, we should use the piece of information that it gives us. It tells us the equilibrium partial pressure of NO2 is what?
0.512.
0.512. Okay, so in that case, has NO2 gone up or down? It's gone down. So, you will not necessarily always put a subtraction sign in front of your reactant change. It could be minus or plus. You have to use the context clues to figure out which it is. In this case, this clearly is going down. So what should I put for the change?
Negative x.
I'm sorry?
Negative x.
Not quite. When you're doing this, you want to keep track of the coefficients. That's a very easy mistake to make. I've made it myself sometimes, so don't feel too bad. So instead of saying minus x, what should I put here?
2x.
Minus 2x. Because it's two coefficient. Now in that case, what should I put over here?
Plus x.
Plus x. So this will then be 1.500 plus x. And this will be 0.512. Oh, now here's the thing. Initial plus the change gives you the equilibrium. So I can actually use this to solve for what my x value would be. I don't even need to use a quadratic equation. Sets it up all nice and easy for me. So 1 minus 2x is equal to 0.512. Do a little rearrangement, and I would get 2x is equal to 0.488 ATM, which means that x ends up being 0.244 ATM. Good deal? Make sense? We're happy? Alright, cool. So now what we're going to do is we're going to go ahead and figure out what our amount is here. If I do 1.5 plus the 0.244, that's going to give me 1.744 ATM. At this point, I can feel free to go ahead and answer part B. Because part A, the question was, what is the equilibrium pressure of N2O4? We've just figured that out by adding our 0.244 to the 1.5. Now, we can go ahead and calculate the Kp for this reaction. It says, now before we can do that, we have to write the equilibrium constant expression. What is the equilibrium constant expression for this? I'm adding a little air to the room, sorry. I was getting a little warm.
It is. Yeah, it is.
Would it be NO2 squared?
NO2 squared. Now it would be the P of NO2 squared, right? Because it's the Kp. And then we would divide that by pressure of N2O4. Now, we could plug in our value, 0.512 ATM squared divided by 1.744 ATM. And we get our lovely answer here, which would be what? Where is thy calculator? What?
1503.
Close enough for government. 1503. Actually, it'd only be 0.150 because we have 3 sig figs. Damn. I'll teach you to correct me. Alright, so now we can proceed to a little Q versus K comparison. Alright, so number 4, we have what's known as a Q versus K comparison problem. So you all know what an equilibrium constant now is, and we've done a little calculation of the equilibrium constants, and we've done a little bit of work with ice charts. But now we have to do some Q versus K comparisons. Now, Q is the reaction quotient. For any given reactant, or for any given reaction, the Q is essentially the same expression as K. It's just that the Q ratio is the ratio at any point in the reaction, whereas K is a constant because it's the ratio only at equilibrium. So the equation given here is N2 plus 3H2 is in equilibrium with 2NH3.
What?
There you go. And these are all gases, of course. Now it says, for each example mixture below, identify if it's going to shift towards the products or towards reactants. And it gives us an initial part A set of values of 105 ATM, NH3, 35 ATM, N2, and 495 ATM, H2. Okay, so then here's the deal. When you're setting something like this up, first thing you want to do is write your equilibrium constant expression. Kp for this reaction is what?
NHD squared, peak pressure of NHD squared over pressure of N2 plus
Times the pressure
of H squared to the third.
H2 to the third. And these are all gases, which I probably should have mentioned earlier. Okay. So now, the thing about this, the Q expression is the same exact thing. P NH3 squared over P of N2 times P of H3, or H2 rather, to the third. So, essentially, if we have a reaction diagram, okay, and let's say the orange line represents, these are your products. That's the amount of products you have, okay? And let's say the blue line represents reactants. These are your reactants. You are tired.
I know. I'm trying so hard to work.
No, I think it's commendable that you showed up when you're feeling so tired. Alright, so here's the reaction. So this is time, okay? As the reaction proceeds, it's going to reach equilibrium, okay? So, you don't necessarily know if products are favored or reactants are favored. We're going to assume, in this case, I happen to know offhand that for this particular reaction, the reactants are heavily favored. And that's because it tells you that the equilibrium constant for this is 4.51 times 10 to the negative fifth. This is 4.51 times 10 to the negative fifth. So this is definitely reactant favored. Products are not favored. But if we were to draw a diagram, and this is not to scale or anything, what happens is, so your products, let's say you start with 0 products, okay? It's going to go up, and then it's going to reach a relatively constant value. And I can't draw a straight line, so it doesn't help, but... Alright. Now, on the other hand, your reactant concentrations started up maybe here, and they go down until they're constant. Now, if you happen to take the ratio of products to reactants at this point here, it's at equilibrium. The net change is 0 at this point because they're going back and forth. Products are becoming reactants and reactants are becoming products at basically the same rate. So they're not actually changing. So if you get it right here, you have K. But you could have gotten it right here. You could have gotten it right here. You could have gotten it right here. Each of these would be a Q, Q1, Q2, Q3. Effectively, Q can be at any point in the reaction, whereas K is always at the point where the reactant and product concentrations have stabilized. Does that make sense? So, what we do, and also, here's the thing, you can also have a disturbance later on. You can also, let's say at this point, let's say I dump a whole bunch, or actually let's say I pull out the products. Let's say I have a way of pulling out the products and getting it into solution. So all of a sudden the product amount drops here. And then it drops suddenly, but then equilibrium comes back to shift it back, okay? Well, now, if the product amount drops suddenly, then that's going to cause, the reactants might have to compensate. They might, initially, if you haven't changed the reactants, when the products drop suddenly, the reactants will have to compensate and convert more to products to restore the ratio, right? Alternatively, you could dump some product into this mixture and then be too product heavy. You gotta pump this up. And then it would immediately go back. Equilibrium would shift to undo that. So if I dump product in, that's going to end up causing this to spike your reactants, to increase the reactants, to basically convert the products into reactants to compensate and restore the ratio. The ratio of products to reactants is always going to be the same. And essentially, at any point where it is not at equilibrium, where it needs to change, Q can represent any of those points. Q can represent any point. Q can also represent a point at equilibrium. But essentially, this ratio can be used at any point in the reaction, whereas K can only be used when it's at equilibrium. I hope I didn't make that more complicated than it actually was. Does that make sense, though?
Yes.
Okay. Good. What?
All of it.
Okay. So, in this case, we're going to go ahead and calculate what the Q value is, and then use that to figure out which way it's going to shift. Okay. So, Q. For A is going to be the concentration of products, NH3, so there'll be 105 APM. Squared over 35 ATM times 495 ATM cubed. Calculate that for me and tell me what you get. You didn't raise it to a power.
I am.
Where are your powers, young lady? What'd you get? Did you get something crazy?
Super low.
Good.
Yeah.
Yeah, you got like
2.6
2.6 times 10 to the whatever. I'm going to shift to scientific notation because I don't feel like doing that work. Alright, 2.60 times 10 to the negative 6. 2.60 times 10 to the negative 6. Alright. Cool? Now the question, you want to figure out which way this ends up shifting. Is Q greater than K or less than K? It's less than K. Now Q is always going to move towards whatever K is. If Q is less than K, it's going to have to increase. If Q is greater than K, it's going to have to decrease. Now which way do you need to shift this reaction to increase the value of Q? If you want Q to get bigger, because it needs to get bigger, right? If you want Q to get bigger, do you need more products or more reactants?
Products.
You need more products. So it shifts to the right. Shift to products. Make sense? That's a rather introspective look on your face.
Oh, I was trying to figure out a way to like shortcut it. Because if someone says you have your Q is smaller than K, then I was trying to figure out if I could just hear Q is smaller, so you gotta go towards the products, or something. I was trying to see if I could remember that.
Well,
it looks like
if Q is less than K, that means Q needs to increase, so it shifts to products. Q is greater than K, that means Q needs to decrease, which means you shift to reactants. So if there are more reactants, Q gets smaller. If there are more products, Q gets bigger. Okay, I'll show you a shortcut. Alright, is it okay if I erase this part?
yeah.
Okay. You can also think of it like this in terms of visual. So if this one particular value is K, and Q can be anything along this range starting from 0 and going to, I don't know, infinity. So if Q is less than K, let's say Q is like only extends as far as here. Or rather, let's say Q is right here. Less than K, it shifts to the right. If Q is equal to K, it's right on the line. It doesn't move. If Q is greater than K, I should just use the greater than symbol.
Yeah.
Here. Q is greater than K, it shift to the left. Easy, right? Who would have thought that the number line would be so useless? I mean useful. Alright, cool. So let's take a look at some more intense ice chart problems, shall we? It says, for number 5, for the equilibrium below, Br2 and Cl2 react to form 2 BrCl, all in the gas phase. I don't know exactly what accent that is, but it's kind of fun. At 400 Kelvin, Kc is 7.0. If 0.30 moles of bromine and 0.30 moles of chlorine are introduced into a 1 liter container at 400 Kelvin, what will the equilibrium concentration of Br2, Cl2, and BrCl be? So, start with Br2, Cl2, equilibrium, 2 BrCl. Now, once again, we know we have to use an ice chart because why? How do we know we have to use an ice chart?
You're given an
Give an initial and you're asked to solve for
the equilibrium.
the equilibrium. So ice chart is appropriate. Now here's the deal. With this, can an ice chart use moles? No. Ice chart must use molarity, concentration. However, in this case, very conveniently, we are using a 1 liter container. So, in that case, since you're dividing the moles by 1 to get molarity, the molarity is the same number as the moles. So it'll be 0.30 molar Cl, or Br2, and 0.30 molar Cl2. And how much BrCl do we have initially? You said something, I think. Or did you not?
Oh,
Oh. Don't let me.
initially?
It-
Zero.
Yeah, it's 0. If it doesn't say how much is present, you can assume it's probably 0. Okay. So, in this case, where's the plus going to be? And where's the minus going to be? Is the plus going to be on the product or the reactant side?
Product.
How do you know?
Because it
It
needs
goes
to
from
be.
0 to,
I don't know.
Because what?
it goes from 0 to,
Can you have less than 0 of something?
No, that would be negative.
No. You can't. You cannot have a negative concentration. You cannot have less than 0 of something. There can't be less than 0 people in a room. There can't be less than 0 chairs at a table, right? So,
This would be positive.
yeah,
so this has to be positive. Now, positive what?
2 plus, or 2.
2x.
Positive 2x. Way to remember the coefficient. What about these guys? What are these going to be?
Minus.
Minus x.
Why is it minus?
Well, because if reactants are formed, they have to be formed, if products are formed, they have to be formed from reactants, right? So if this increases, these necessarily have to decrease. Yeah.
Wait, what?
In a reaction, one side always increases, the other side always decreases. For products to form, they have to be formed from reactants. You can't build a table without any wood, right?
Yes.
I guess you could build it out of metal, but you know what I'm saying. You need to make a cake. You're going to have to use some sort of flour, probably some eggs. You know what I'm saying? You can't. You're not just going to have a cake pop out of nowhere, right? That'd be nice if it happened, but then,
Unless you're magic.
yeah. Well, we're scientists. We don't believe in magic. All right.
Where's your childlike whimsy, sir?
So this is 0 plus 2x is 2x. And this is 0.30 minus x. 0.30 minus x. Alright, so here's the deal. Now, you can set up our equilibrium constant expression. In this case, we're going to do, it says Kc, so we're going to do it in terms of concentration. Because technically these are pressures. These are all, well, are they gases? Yeah, they're gases. These are all gases, so we could do Kp if we wanted to, but in this case it gives us Kc. So we're going to use Kc. So what is the equilibrium constant expression in terms of concentrations here?
Oh.
It's 2x squared.
Br, concentration of BrCl, squared to over
Concentration of Br, 2B2, and CO2.
CO2. Very good. If I didn't know you were tired, I would swear you were bored out of your mind.
No. I actually needed. I need to learn this because I haven't been understanding any class.
And
So.
no judgment, I understand.
So.
Alright, so 7.0 is,
That's the only thing I have trouble.
so I go ahead and pop this in.
No,
I,
there's no.
a 7.0, I plug in my value for Kc,
Uh-huh.
and then I plug in my values,
For
equilibrium for this, and I'm going to solve for x. So in BrCl2, this is going to be 2x, and then we'll raise it to the squared power, and then on the bottom, I have 0.30x, or 0.30 minus x, rather, times 0.30 minus x.
So.
Now, because this is the same, it's squared, and so I could rewrite this, like you said, as 7.0
Equals
2x squared
over 0.30 minus x squared.
Alright, now, if you wanted to, you could FOIL this, bring it over to the other side, set it equal to 0, throw it into the quadratic equation, and solve it. But, I have a feeling you don't want to do that. So, instead, we're going to do what I like to call the easy way. we're going to go ahead and recognize these are both squared, so I can take the square root of both. And that gives us 2x
Both squares.
over 0.30 minus x is equal to the square root of 7. What? I didn't hear what you said, I'm sorry.
It's much easier.
Oh yeah, definitely. And so now I'm just going to multiply both sides by the denominator, because I don't like to deal with fractions, and you can't solve for x and it's in the denominator. So let that be a lesson to you. You cannot solve for x when it's in the denominator. So that cancels out that, and I'm left with 2x equal to whatever the heck that is. So 2x is equal to, and I'm going to distribute this, I have to distribute this. Bring your algebra skills. And you're going to have 0.3 square roots of 7. Whoops. 7. Minus the square root of 7 times x. And then I'm going to go ahead and add square root of 7 times x to both sides, so I get 2 plus the square root of 7 times x equals 0.30 square roots of 7. And then I'll divide both sides by 2 plus the square root of 7. 2 plus square root of 7. And there you go. So x is equal to whatever the heck that is. Pop it into your calculator, and truthfully speaking, if you really wanted to, you could have actually resolved this in your calculator into an actual number a long time ago. But, you know, what fun would that be?
Tons of fun. That would have been great.
Calculate it for me, calculate it! So 0.17.
Yes.
Yes.
I was going to say, if you got 1.7, we might have a little problem here.
Yeah.
Yeah. So yeah, no, 0.17 sounds good, which means that this would be 2 times 0.17, or 0.34 molarity, or this would be 0.30 minus 0.17 equals 0.13. Notice, 0.17 was not your answer. It was not your final answer. So, if you're given a multiple choice question like this, one of the most common mistakes that I've seen students make is that they'll do all this work and they'll do such a good job and they'll get the right value of x, and then that's what they put in for their answer. So that's what they select from the answer choices.
So what are we solving for? Dumb question.
Because what is it asking for? It's not asking for 0.17, it's not asking for x, it's asking for the equilibrium concentrations.
There it is.
And it may, like in a multiple choice question, they might ask you, what is the equilibrium concentration for Cl2? In which case you're like, oh, I have to subtract that. Or, if equilibrium concentration for this, I have to multiply by 2. So you just have to look at what it's asking for, because it's very easy to make mistakes on that. Cool? Let's go ahead and do the last and final problem of our little excursion. Alright, so we got pH3, BCl3.
It's like this long MCAT.
I'm going to have to edit out all this extraneous conversation from the final video cut. So. Actually, I might just leave it in for fun.
They're gonna need it. This is soul crushing.
There you go. Alright, so now we have our lovely little equation here, and it says, calculate the concentrations of pH3 and BCl3 if a solid sample of pH3's BCl3 is placed in a closed vessel and decomposes until equilibrium is reached. Now it does actually give us the Kc value here, which is 1.87 times 10 to the negative 3. So how would I begin to solve this? It wants to know what is the concentration of these guys.
So we do need an ice table.
You do need an ice table, we can do that. So ICE. What's the initial concentration of this?
0.
0? What's the initial concentration of this?
0.
0? And what's the initial concentration of this, or do we not care?
Do not.
No, we don't care.
Okay. It's a solid. Nobody cares.
Cool.
Now, what's the change going to be?
Positive?
Positive. You can't very well have a negative change, right? And the coefficients are 1, so it'll be positive x. So you have x and x.
Why can't it be negative?
You can't have less than 0 of something.
Oh. Yep.
Okay. So what is the equilibrium constant expression? What's the equilibrium constant expression here?
pH.
How have I mentioned how much I appreciate your presence here? It kind of lightens the mood, you know? Alright. Kc is what?
What do we?
pH.
pH3, concentration, right?
Concentration of C.
And times concentration of what?
BCl3.
BCl3. Now remember when I told you about the equilibrium constants having more to do with activity? And equilibrium constants for concentration of products over concentration of reactants? If this truly was a non-entity, you'd be dividing by 0. Only Chakravarti does that. So now, you understand that yes, this is actually being divided by 1. Because the activity of all solids and liquids is assumed to be 1. The activity of solids and liquids is assumed to be 1. So in this case, this is divided by 1, which means we can just leave it as is. Alright, so now we have an equation, pretty easy to solve. All we have to do is plug in our values, which is 1.87 times 10 to the negative 3rd is equal to x squared, right? And we just take the square root. Bam, bam. X equals what?
I got 0.04324.
0.043 what?
24.
Okay, so 0.0432 would be sufficient here with 3 sig figs. So 0.0432 molar. So that is the molarity that this has to be. Now here's an interesting point though. This C value here is still minus X. We just don't care what the initial concentration and the final concentration are. But if there's not enough of this to produce this, then it will not reach equilibrium. Or rather, it will not reach the equilibrium concentration. So, now that brings us to our second problem. The second part of the problem, D, it says if the flask has a volume of 0.500 liters, what is the minimum mass of pH3BCl3 that must be added to the flask for equilibrium to be achieved? It's actually a little easier than you might think. Because we know that we need this level, this molarity of pH3 and BCl3, right? Which means that we need 0.432 moles per liter of this. Even though this is a solid, it's not going to be a concentration per se, but we know we need that many moles. We can figure it out based on what the volume is. It gives us the volume as 0.500 liters, right? So I can use my molarity to calculate the number of moles that I'm going to need. So 1 liter is 0.432 moles of pH3 BCl3. And even though strictly speaking this isn't really a concentration of this, it is going to still tell us the amount that we need. Why not? No,
Good answer.
because I know that alternatively what you could do is you could say, well, I can convert moles of, I can use the molarity to convert liters to moles of pH3, right? Because this is the molarity of pH3, right? It's also the molarity of BCl3. And then I could do another conversion factor and convert moles of pH3 to moles of pH3 BCl3. And to throw back to the old stoichiometry, the 1-to-1 ratio. And then from there, all I have to do is convert moles of pH3 BCl3 to grams pH3 BCl3. And to do that, I need the molar mass. What's the molar mass of pH3 BCl3?
Yep, it's 151.
It's 151.
Yeah.
Okay.
How dare, what are you teaching us?
So there you go. You can multiply everything on top and divide by the bottom, and that will give you the value. That will give you how much pH3 BCl3 must be present in the flask to begin with in order to enable it to achieve equilibrium. Cool. Good job.